Hello, this video is going to talk through the review problems for the Unit 1 Investigation 3 quiz. So looking back at Lesson 1, our first topic was atomic theory and how the model of the atom has changed over time. So we want to review some of those atomic models. Don't worry about memorizing names of scientists, that part of it's not important. We're looking at more how evidence fits with models and how models have changed over time. So for problem number 1, describe the results that led Rutherford to come up with a nuclear model of the atom. So the nuclear model of the atom is that the atom is mainly empty space and there's this tiny dense nucleus here in the middle. And the evidence that led to this model was, we don't need to get too much into details here, but remember he had that experiment where he shot these kind of particles at the atom. And remember at this point people thought that the atom was just kind of like a gooey, jello-y like thing. And they saw that every once in a while some of those particles would bounce back. And that told them that, since most of the particles went straight through, that means that the atom is mostly empty space. And you might remember from the video that there was that example that the guy used, and he said that if you took out all the empty space and all the atoms in your body, you would shrink down to the size of smaller than a grain of salt, but you'd still have the same mass. So it'd be an incredibly heavy grain of salt, very, very dense. But atoms are mainly empty space, and there's this small, dense nucleus in the middle. And so there's a small, dense thing in the middle, and they decided to, call that thing the nucleus. And they could tell that it was there because, again, some of these particles bounced back instead of going straight through. So there must have been something there in the middle that they were bouncing off of. So that's the nuclear model of the atom. Looking at a couple other models, look at the electron cloud model versus the planetary model. So in the planetary model, the idea is that the electrons are like these, they're like planets orbiting the sun. So the electrons orbit around the nucleus like planets orbiting around the sun. Versus the electron cloud model, the idea there, remember this is like what our popcorn demo was. It was like, we had all these dots represented that the likely place where electrons might be. So in this model, we don't know the exact location of an electron. We have this probability cloud. And so these electron clouds represent a place in which an electron might be. We don't know exactly where it is. It's just kind of like in class, that basically map we made with the Jiffy Pop could be used as a way to guess where a piece of popcorn might land when you're popping the popcorn. So we don't know for certain where the electrons are, but we know they don't orbit around the nucleus. They're just kind of somewhere. So it's a much vaguer model, but it's actually the more accurate model. It fits with our current understanding of what's going on with physics and stuff. So electron cloud models are most current model of the atom. All right, let's look at this last one, billiard ball model versus plum pudding model. So the billiard ball model is it's just like one, indivisible thing. And so it would be solid, it's just one thing, there's no smaller parts to it, versus the plum pudding model of the atom was the idea, remember we had the jello, and fruit chunk idea. It was the idea that there's this positive goo with these negative electrons floating around. So the atom's made of positive goo with negative electrons floating around in it. Okay. So let's scroll down here and start thinking about isotopes. So, I just realized there's a typo here. So stable isotopes of magnesium occur naturally. That's a typo. It shouldn't say neon. So we've got 3 isotopes of magnesium. Magnesium 24, 25, 26. Remember, these numbers right here represent the mass number, which is how heavy one atom is, and the mass number is the number of protons plus the number of neutrons. Okay, so first thing we're going to do is we're going to go through and determine the subatomic particles in these three isotopes. So the number of protons, since it's magnesium, you look up on the periodic table, magnesium, and the number of protons is the atomic number that's on the top there of your periodic table. So since they're all magnesium, they all have 12 protons, because the atomic number of protons defines what the element is. Number of neutrons you get from taking the mass number minus the number of protons, because remember we said up here protons plus neutrons gives us the mass, so we can subtract protons to get neutrons. Okay, so this is going to be 24 minus 12. It's got 12 neutrons. This is 25 minus 12, so 13. 26 minus 12 is 14. So those are our numbers of neutrons, and then the electrons are always equal to the number of protons. Running out of room here, but electrons are equal. These two guys are equal to each other. And the reason why is because protons are positive, electrons are negative, and we know that atoms are neutral. Okay, so in a neutral atom, protons have to equal your electrons. So your positives need to equal your negatives. And then the way you write the symbol is we write the atomic number on the bottom and the mass number on the top. So magnesium looks like that. So we got three versions of magnesium. Okay, here we go. So that's that table. So let's look at B. If you were to pick up and weigh one single atom of magnesium, it would most likely weigh what? Well, if we look up here at this table, we can see from the table what the most common isotope of magnesium is. And it looks like it's this one right here. It has the, whoops, we'll scroll down here. Okay, it looks like magnesium 24 has the highest relative abundance. Okay, so it will most likely have a mass of 24, and that means it would most likely have 12 neutrons, as we determined right up here. So it is the most common isotope. And there's two ways in which we can figure that out. One way is just from looking up here at the table. This tells us that it's the most common isotope, so it's got the highest relative abundance of any of the three isotopes. The other thing you might do too is if you look at the periodic table and find the average mass, which we're actually going to calculate next, but if you look at the average atomic mass, which is below the symbol, it's going to say 24.3, and you'll notice that this is closest to 24 than any of my other masses. So that's another hint that having a mass of 24 is the most common version of magnesium. All right, so let's calculate the average atomic mass. Sorry with my scrolling here. So the way that you find the average mass is you take the percent abundance times mass for as many isotopes you have. You want to first convert that percentage into a decimal. So I'm finding my average. I'm going to take 79%. I'm going to convert that into a decimal, so 0.79, multiplied by the mass, which is 24. Then 10%, convert that into a decimal, that's 0.10, times 25. And then 11%, convert that to a decimal, times 26. And then I'm going to add all those up, and I don't have my calculator with me, but it should end up being 24.3. It should match what's up on the periodic table. So notice that since having a mass of 24 is your most common version of magnesium, your average mass is going to be closest to 24. Okay. All right, so the number of electrons in a neutral atom is the same as the number of protons, because electrons are negative, protons are positive, so your negative charges, in order to be neutral, you need to have your, negative charge and positive charge equal. So like if you have one positive and one negative charge, that adds up to 0. Okay, so if you have like 3 protons, you need to have 3 electrons in order to add up to 0. So positives and negatives need to add up to 0, so your protons must equal your electrons. All right, and then number 4, here's another average atomic mass problem. So again, I'm going to take my percent abundance right here. I'm going to turn that into a percentage, into a decimal, so 0.374% times 185. And then I'm going to take my other percentage here, 0.62. So 62.6%, turn that into a decimal, multiply it by, okay, there's 187. So what's this saying is 37.4% weigh 185, and then 62.6% weigh 187. And if you add those up, you should find the average atomic mass of rhenium, which, yeah, unfortunately I don't have my calculator with me, but I would think that that adds up to, let's see, 186.2. That's what it looks like from the periodic table, so that's what that should add up to. And notice here that the average mass is closer to 187 than to 185, and that makes sense because this is the more common version of rhenium. Okay, and then looking at 5 here, again, uses that logic that we were just thinking about in the previous problem. So look at the average atomic mass of this element. So like for boron, I'm going to look on the periodic table, and the average atomic mass of boron is 10.8. So I find that in the periodic table. Then you ask yourself, which is that closer to? Is that closer to 10 or 11? In this case, it's closer to, the average is closer to 11. So that means most of the boron atoms in the world must weigh 11. A few of them weigh 10, so the average is going to be closer to 11 than 10. Okay. Nitrogen's average atomic mass is 14.01. That is very close to 14, so I'm assuming this is the most common version of nitrogen. Chlorine's atomic mass is 35.45. That is closer to 35 than it is to 37. Nickel average is 58.69. So that means nickel 58 must be the more common version of nickel. And then sulfur 32.06 is its average. So that tells me the isotope with a mass of 32 is more common. So again, you're looking for the isotope that is closest to your average. And then sodium is 22.99. This is closer to 23 than to 22. Okay. And look at number 6, and then we'll pause this one, and I'll have another video for the last few questions. The mass number is the number of protons plus the number of neutrons. The average atomic mass is the one that's on the periodic table, and it's the one that you find using this math up here. So you find using isotope masses and abundances. All right, so I will make a second video going over the rest of this, and hope this helps.